In this lesson, we're going to continue our look at radicals, moving beyond halogenation and exploring some other reactions that involve radicals as intermediates. We've seen that radical bromination is regioselective, preferring to replace the hydrogen on the most highly substituted carbon in the molecule. This results in the most highly substituted and therefore most stable carbon radical. But we've also seen that resonance can greatly stabilize radicals, such as seen with the allylic radical. We might then expect the radical halogenation of propene to proceed to give 1-bromo-2-propene as the major product. The reaction would proceed through hydrogen atom abstraction from the allylic carbon to give the highly resonance stabilized allylic radical. While this reaction does in fact work, it's complicated by a second reaction that you're probably already familiar with, and that's electrophilic halogenation, the addition of Br2 across the pi bond of the alkene. This means that treatment of an alkene with a dihalide results in a mixture of products, from radical halogenation and electrophilic addition. Radical halogenation at the allylic site can, however, be achieved using a different set of reaction conditions. Specifically, using N-bromosuccinimide, or NBS, promotes the radical halogenation to the exclusion of the electrophilic addition. And that's simply because there's no dihalide present in the reaction to promote the electrophilic addition. Keep in mind that radical halogenations that proceed through an allylic radical often give a mixture of substitution products. Here we see a simple example using 1-butene. The allylic radical formed as an intermediate has two electrophilic carbons, and halogenation can occur at either site, in this case giving a mixture of 3-bromo-1-butene and 1-bromo-2-butene. Another reaction that involves radicals as intermediates is the hydrobromination reaction in the presence of a peroxide. You might recall that addition of HBr to an alkene typically proceeds with Markovnikov regioselectivity. Here we see an example with propene reacting to give 2-bromopropane. The reaction involves the formation of a carbocation intermediate, and the more stable, more highly substituted carbocation is formed more quickly. In this case, the halogen ends up bonded to the more highly substituted carbon of the original alkene. The regioselectivity can be reversed by introducing a peroxide to the reaction conditions. A peroxide is a molecule that has an oxygen-oxygen single bond. You're probably familiar with hydrogen peroxide, H2O2, which is the simplest peroxide. HBr addition to an alkene in the presence of a peroxide proceeds with anti-Markovnikov regioselectivity. In the example here, you can see that propene reacts to give 1-bromopropane, placing the halogen on the less substituted carbon of the original alkene. This phenomenon is known as the peroxide effect, and it's important to recognize that it only works with hydrobromination, the addition of HBr. The reaction mechanism involves the formation of several radical intermediates and explains the reversal of regioselectivity. The first step is the homolytic cleavage of the oxygen-oxygen bond in the peroxide to give two oxygen radicals. This radical then abstracts a hydrogen atom from HBr to give a bromine radical. In the first propagation step, the bromine radical cleaves the carbon-carbon pi bond of the alkene to create a carbon-bromine bond and a carbon radical. It's in this step that the regioselectivity of the reaction is established. Placement of the bromine on the less substituted carbon of the alkene results in the formation of a more highly substituted and therefore more stable radical. Attaching the bromine to the more substituted carbon of the alkene would result in the formation of a less substituted and therefore less stable radical. In the second propagation step, the carbon radical abstracts a hydrogen atom from HBr to give the final product and another bromine radical. Once again, the two propagation steps form a chain reaction. The second propagation step produces a bromine radical which is required for the first propagation step, and the first propagation step produces the carbon radical required for the second propagation step. The reaction proceeds until one or both of the starting reagents are consumed. Occasional termination steps, which combine two radicals into a non-radical, will also occur. The last radical reaction we'll look at is the metal-ammonia reduction, a reaction you might have seen before. The metal-ammonia reduction is the reaction of an alkyne with an alkali metal, such as lithium or sodium, in liquid ammonia to give a trans alkene. In the example, we see 2-butyne reacting to give trans 2-butene. This makes the metal-ammonia reduction an anti-stereoselective net addition of hydrogen across an alkyne. It's important to remember that this reaction only works on internal alkynes and not terminal alkynes. Remember that an internal alkyne places the triple bond away from either end of the carbon chain. The reaction is performed at cryogenic temperatures, often utilizing dry ice to cool the reaction down to -78 degrees Celsius. The reaction mechanism involves both radical and polar mechanistic steps, employing a mix of both single-barbed and double-barbed curved arrows. In the first step, the metal contributes one electron into one of the pi bonds of the alkyne, forming a radical anion. The unstable carbanion then undergoes a simple acid-base reaction, removing a proton from ammonia to create a new carbon-hydrogen bond. A second equivalent of the metal contributes an additional electron into the remaining carbon radical to give a second carbanion. Just as before, the unstable carbanion undergoes a simple acid-base reaction, removing a hydrogen atom from ammonia to give the final product.